Good evening, everyone. Good evening,
Good
Sharmila.
evening.
Good evening, Kana. So, we have been discussing electrochemistry, right? So, what are the stuffs we have discussed in the last class? Good evening, Sandhamir Chelvan. So, we have discussed the working principle of galvanic cell, and we have discussed what is electrode potential and types of electrode potential. And today we have to start with the physical significance of electrode potential, right? So, basically, what is electrode potential? Electrode potential. What is electrode potential? Okay, what is the basic principle of galvanic cell? In which we have discussed the working principle of Daniel cell also, but I just want the basic fundamental concept of galvanic cell, how it works, or what is the principle over there in galvanic cell, or what kind of reaction we can expect in galvanic cell. Yes, Rakshan.
Spontaneous reaction.
Yes, Kana, what is your name?
Reaction.
Rakshan. Okay. Spontaneous reaction, and Sendavil Chelvan's answer is it is a cell where chemical energy is getting converted into electrical energy. So both answers were perfect. So in galvanic cell, we have discussed one of the cells which is called Daniel cell, in which we have zinc electrode and copper electrode, and in zinc oxidation occurs and in copper reduction occurs, and there was a flow of electron from zinc to copper. So because of which current were moving from copper to zinc, right? And we have discussed what is that cell potential and all that, right? Fine. So basically, electrode potential is nothing but if you dip any metal in its own electrolytic solution, there will be a charge separation between electrode and electrolytic solution, right? Because of that charge separation, a potential is developed, and that potential is called electrode potential. If that potential is due to oxidation reaction, that is oxidation potential. If the potential is developed due to reduction reaction, then that is called reduction potential. These are all the stuffs we have discussed already. And I just want to ask you, between these oxidation and reduction potential, which is the potential which we'll be using in our numerical? Among these potentials, as I told only one potential can be used throughout the numerical or in any shortcuts. What was that? Though we have two types of potentials, we'll be using only one type of potential in our numerical, which is that?
Reduction potential.
Very good. Reduction potential. Right. So, in a problem, if we are provided with oxidation potential also, we have to convert that into a reduction potential. Okay. Have to convert oxidation potential to reduction potential. Have to do that. Have to convert oxidation to reduction potential. Yes, by just changing the sign. If the value is negative, then we have to convert that into positive. If the oxidation potential is positive, then we have to convert that into negative. That's it. I'm going to give you a representation, and from which you have to tell me whether the potential is oxidation or reduction potential. The representation is E naught Okay, I've given a potential of a metal M, and I want you to tell whether this potential is oxidation potential or reduction potential. Have to find whether this potential is oxidation or reduction potential. See the representation. We cannot identify with the sign of the value, but we can identify with the representation. See, it is E naught Mn plus slash Mn. or I'll give you a particular metal at least. Now tell me, is it oxidation potential or reduction potential?
Reduction potential, ma'am.
Very good, it is reduction potential because here Zn2 plus is getting converted into zinc. So Zn2 plus has to gain 2 electrons to get converted into zinc. So it is basically gain of electron. Gain of electron is called reduction. So this value is a reduction potential. Okay. Similarly, here M is in plus N oxidation state, and here it is in zero oxidation state. So this N plus has to gain N times of electron to get converted into M. So the 0.86 is the reduction potential of this metal M. Fine. And how to measure this electrode potential? We have been, I told about a reference electrode. Could you please name that reference electrode? We have to connect the unknown metal with the... Come again, Rakshan?
Standard hydrogen electrode.
Very good. Standard hydrogen electrode, which is abbreviated as SHE, S-H-E. So we have to connect this unknown metal with standard hydrogen electrode, and we have to find the reduction potential of the unknown metal. Fine. And I want to give you an activity for next class. I want you to study the working principle of SHE, which is standard hydrogen electrode. I want you to find what is the electrolytic solution, what is the electrode used in SHE, and the concentration of the electrolytic solution and all that. Okay. So study the working principle of standard hydrogen electrode. Okay, fine. So last class we have discussed till this reduction potential, right? And today we're going to start with the physical significance of this electrode potential. In your exams, they'll give you this electrode potential values, and they may ask you different types of questions. For example, last class I discussed about this Daniel cell, right? Where I had zinc and copper metal. Among zinc and copper, the metal which was oxidized was zinc, and the metal which was reduced was copper, right? In your exam, they may give you two different metals. Here I've given zinc and copper. If we are provided with the metal like zinc and copper, you will find zinc will get oxidized and copper will get reduced. But in your exams, if they give you any other two metals, then we have to find which metal will get oxidized and which metal will get reduced. And also we have to find the electron flow direction, current flow direction, and also we should be in a position to calculate the cell potential also. For Daniel cell, what was the standard cell potential? What is the standard cell potential of Daniel cell?
0.0 volt.
That is for SHE. But I'm asking for Daniel cell. E0 cell of Daniel cell. Very good. Sendamil children's answer is right, which is 1.1 volt. In your exams, they may give you any other two metal, and they may ask you to calculate the value of E0 cell. So for all these, we have to use this electrode potential. So I'll give you the shortcut to find all these stuffs. Okay. For example, I have a metal M1 and I have a metal M2. For example, the reduction potential value of M1 is minus 0.74 volt, and the reduction potential value of M2 metal is plus 0.23 volt. See, here I've given only reduction potential. In your exam, if we are provided with any potential, please check whether the value is reduction potential or not. If it is not reduction potential, please convert that into reduction potential by changing the sign. Fine. Here I have metal M1 and M2 and their reduction potentials as well. So now we have to find which metal will get if we connect M1 and M2, we have to find which metal will get oxidized and which will get reduced. For that, please use the shortcut negative terminal and positive terminal. I'm going to connect this negative and positive terminal. Could you please tell me electron will be, from which direction to, or which point to which point electron will be moving? From negative to positive or positive to negative? How this electron will flow?
Negative to positive.
Very good. Since electrons are negatively charged species, these negatively charged species will move towards positively charged site. So electrons will be moving from negative charge to positive charge, or negative site to positive site, or negative terminal to positive terminal. So let us say this is a system X or metal X, and this is metal Y. So electrons are moving from X to Y. So basically the metal Y is gaining electron. If a metal gains electron, then that process is called, if a metal gains electron, then that process is called, gain of electron is called reduction, right? So how this metal Y is getting reduced, or how this metal Y is gaining electron? Who is losing its electron? Since the metal X is losing its electron, that electron is coming from X to Y. So that is why the metal Y is getting reduced. So what is happening to X? Basically, X is losing its electron. No? So loss of electron is called? Loss of electron is called oxidation. If the metal which is undergoing oxidation, then that metal is anode. If the metal is getting reduced, then that metal is called cathode. Fine. So here X is anode and Y is cathode, right? So X is getting oxidized and Y is getting reduced. Now could you tell me which is the oxidizing agent and which is the reducing agent? What is oxidizing agent? The reagent which is responsible for oxidation is called oxidizing agent, and that reagent will get reduced, right? That reagent itself will get reduced. So based on that concept, among X and Y, could you please tell me which is the oxidizing agent and which is the reducing agent? Among X and Y, which was oxidized? Which was oxidized?
Oxidizing agent.
Y is?
Oxidizing agent.
Very good, Rakshan. So here X is oxidizing, and for this oxidation process, Y was responsible. So here Y is the oxidizing agent. So oxidizing agent is the reagent which is responsible for the oxidation, and it will reduce itself. And similarly here X is responsible for the metal Y to get reduced. So here X is the reducing agent. That's it. And they may ask you, among X and Y, which metal is considered to be highly reactive metal? Okay. Basically, the metal which is getting oxidized is considered to be highly reactive. So among X and Y, which is considered to be highly reactive then?
X is highly reactive.
That's it. So this is highly reactive. So from the shortcut, we can answer so many questions. Okay. So if the electrons are moving from X to Y, then what will be the direction of current flow? What will be the direction of current flow? Current will be moving from Y to X. Fine. Is that clear? Okay. Now could you please tell me, among M1 and M2, which will get oxidized and which will get reduced? So please apply the same shortcut here. The values minus 0.74 and another values plus 0.23. So electron will be moving from negative terminal to positive terminal. So please tell me which metal is getting oxidized and which is getting reduced. Yes, Sendamit Shelvin's answer is right. The metal M2 is gaining electrons, so it is undergoing reduction, and this is undergoing oxidation. The electrode which is getting oxidized is considered to be anode, and this is considered to be cathode. Fine. Among M1 and M2, which is highly reactive metal? which is considered to be highly
M1 is
reactive.
highly reactive.
Very good, M1 is highly reactive. That's it. Okay. If suppose I have a metal M and a metal N, or P and Q, and the reduction potential value is 0.23 and 0.19 volt. See, in this example, the electrode potential of one metal was negative, another metal was positive. So the shortcut was little easy. Here, both the values were positive. So in such cases, you have to visualize electron flow like electron will be moving from lower value to higher value. Okay, so here minus to positive, right? So initially I told electron will be moving from negative terminal to positive terminal. So basically negative terminal is considered to be the lower value, okay, and positive terminal is considered to be the higher one. So here electron will be moving from which metal to which metal?
Metal Q to metal P.
That's it. So electron will be moving from Q to P. So among P and Q, which is anode and which is cathode? Which is anode and which is cathode?
Metal Q is anode, metal P is cathode.
Very good. So this is anode and this is cathode. So this was oxidized, this was reduced. Could you please tell me which is the oxidizing agent and which is the reducing agent? Which is oxidizing and which is reducing agent?
P is oxidizing agent, Q is reducing agent.
That's it. And this is reducing agent. Okay. I have metals A and B. Reduction potential value of A is minus 1.3 volt and this is minus 0.93. Here, both the values are negative, and among these two values, which is considered to be the lowest one? Which value is considered to be the lowest one? Minus 1.3, right? And Sendamai Chelvan's answer is right. Electron will be moving from lowest value to highest value, right? So, rest of the parameters you can find, right? Which is anode, which is cathode, electron flow, current flow direction and all, we can predict from this direction, right? Any doubt? Now, do you have any doubt till now?
No, ma'am.
Okay. Shall we discuss few numerical related to this electrode potential?
Yes, ma'am.
Okay. And also, we have predicted the anode, cathode, electron flow, current flow direction and all that, right? Similarly, we can also calculate the cell potential. For example, if we connect M1 and M2 in a cell, for which we'll be having the cell potential, right? We can calculate the cell potential, and here is the formula. E naught cell is equal to E naught cathode minus E naught anode. This is the formula. So we know that among M1 and M2, the metal M1 is getting oxidized. So this is the anode, and M2 is getting reduced. So this is the cathode. So we can calculate the cell potential of the first system. Here, this is M2 is the cathode, and the value of electrode potential of cathode is 0.23 minus value of anode is minus 0.74. So if you simplify this, that will be the value of standard cell potential of this cell 1. Okay. Similarly, we can calculate the cell potential of these cells also. Okay. So formula is E naught cathode minus E naught anode. Fine. Do you have any doubt? Any doubt, Kanna?
No, ma'am.
Right. For spontaneous reaction, what is the sign of delta G? A spontaneous reaction, what is the sign of delta G? Negative, right? Similarly, what is the sign of E naught cell? A spontaneous reaction, what is the sign of E naught cell?
Positive.
Positive, right? So, in a question, they may give you the reduction potential values of the metals, and they may ask you whether that cell contains spontaneous reaction or not. So, in such kind of scenarios, you have to find the E naught cell, and from the sign of E naught cell, we can predict whether the reaction is a spontaneous or a non spontaneous one. If that is a spontaneous reaction, then they are talking about galvanic cell. If the reaction is a non spontaneous reaction, then they are talking about electrolytic cell. Fine. So now the numerical is Can anyone please read out this question?
Predict whether the following reaction can occur under standard condition or not.
Okay. Thanks, Kanna. So here we are provided with some chemical reaction, and we have to predict whether this reaction is a spontaneous reaction or non-spontaneous reaction. If that is a spontaneous reaction, then this kind of reaction can occur. If that is a non-spontaneous reaction, then this reaction will not occur. That's it. Okay, but here the data is about E naught, that is the reduction potential of tin and reduction potential of bromine. So to find the feasibility or the spontaneity of the chemical reaction, either we have to find the value of delta G or the value of E cell. According to the data, we can find only the value of E naught cell, right? So what is the formula to calculate E naught cell? Formula to calculate E naught cell? E naught cathode minus E naught anode. Okay, so from this given value, please find which is anode and which is cathode. Before that, we have to confirm whether the values are reduction potential. Reduction potential. So please confirm whether it is reduction potential.
Yes, ma'am, it is reduction potential.
Yes. Here, tin is in 4 plus oxidation state, / here tin is in 2 plus oxidation state. So 4 plus to 2 plus, tin has to gain 2 electrons. So it is basically gain of electron reduction. So this is reduction potential. Here it is bromine, and this bromine is gaining electron to get converted into Br minus. So this is also gain of electron reduction. So this is also a reduction potential. So here both the values are reduction potential. So we can use this data. Now from this value, we have to find whether tin is an anode or cathode. Could you please tell me which is anode and which is cathode? We know the shortcut, right? Which is anode, which is cathode. Here both the values are positive. So the shortcut is electron will be moving from lower value to higher value. Among these two values, which is considered to be the lower one?
Minus 1.06.
Kanna, it is not minus 1.06. The value itself is 1.06. That is Br minus. The negative sign is for bromine. Okay. Sendamil Shelvin's answer is 0.91. Okay, fine. We'll see. Bhumika, among 0.15 and 1.06, which is considered to be the lower value? Which is the smaller one?
Yes, ma'am.
Which one is a smaller value, Kanna? 0.15, right? So electron will be, yes, 0.15. So electron will be moving from 0.15 to 1.06. So bromine will be gaining electrons. So this is reduction. So it is considered to be cathode. So it is getting oxidized. So this is anode. Okay, so what is the cathode value? It is 1.06 minus anode value 0.15. So if you subtract 1.06, if you subtract 0.15 from 1.06, what is the E naught cell? As Sendamil Shelvan told, the value is 0.91. Right. Here, according to our prediction, tin will get oxidized and bromine will get reduced, and the reaction is also the same, right? Sn2 plus is getting oxidized to Sn4 plus, so it is oxidation, and Br2 is gaining electron to get converted into Br minus, so this is reduction. So here, the sign of E naught cell is positive, so this reaction is considered to be the spontaneous one. So this reaction can occur. Fine. Is that clear? Is that clear? Fine. Okay. So here we found the value of E naught cell, right? So for this kind of reaction, what will be the sign of delta G? What will be the sign of delta G? The sign of E naught cell is positive in this case, right? Could you please tell me the sign of delta G?
Negative.
Negative, right? So here we'll write the relationship between delta G and E cell. Delta G is equal to, or delta G naught is equal to minus NF E naught cell. Okay. So delta G naught is nothing but change in standard Gibbs free energy. And E naught cell is your cell potential. What is this F? What is this F? It is a constant. It is called Faraday. Okay. And 1 farad is equal to 96,500 coulomb per mole. Kana, is this the first time you are seeing this value or seeing this constant? Have you heard about this farad in physics at least?
No, ma'am.
Okay, so this is the first time. Okay, right. Now we'll see how this 96,500 value came. Okay. Basically, what is the charge of an electron? For example, I have one electron, and what is the charge of one electron? What is the charge of an electron?
3.2 into
No,
10 to
no, Kana, no. 1 point. 1 point. Charge of an electron. Yes, Sendamil Chelvan's answer is right. 1.6 into 10 power minus 19 coulomb. So charge of one electron is 1.6 into 10 power minus 19 coulomb. So what will be the charge of two electrons? 2 into 1.6 into 10 power minus 19 coulomb, right? So similarly, what is the charge of Avogadro number of electrons? What is Avogadro number? 6.023 into 10 power 23 into 1.6 into 10 power minus 19 coulomb, right? So the charge of one electron is 1.6 into 10 power minus 19 coulomb. So similarly, charge of Avogadro number of electron is 6.023 into 10 power 23 into 1.6 into 10 power minus 19 coulomb, right? Could you please multiply those values? I want you to tell me the approximate value. You just multiply this 1.6 into 6. That's it. So if you multiply these two values, value will be around approximately 96,500, and the unit is charge. The unit of charge is coulomb, and it is the charge of 1 mole of electron, right? So it is coulomb per mole. Okay, Sendamil Chelvan, you asked for the unit, right? It is coulomb per mole. Okay, coulomb per mole. Fine. So this is the relationship between delta G naught and E naught cell. If we have the value of E naught cell, then we can find the value of delta G naught. So for which we have to know the value of N. N is nothing but number of electrons involved. Later I'll teach you how to find this number of electrons involved, okay? But this is the relationship between delta G naught and E naught cell. Okay. Do you have any doubt? If no, then we'll move on to next problem. Any doubt? Sharmila, Bhumika, Rakshan, Sendamil Chelvan, any doubt? Shall we move on to next numerical? Next problem? Fine. Yes, here we are provided with some values and they're asking us to find among these 4 values or 4 elements, they're asking us to find the strongest oxidizing agent. We have to find which is the strongest oxidizing agent. Okay. And we are provided with some electrode potential. Before getting into the problem, we have to find whether the values are oxidation potential or reduction potential. How about this first value? Is it oxidation or reduction potential?
Reduction potential.
Yes. So here chromium 3 plus is getting converted into chromium. So it is a reduction potential. And how about this chlorine? Cl is getting converted into Cl minus. So this is also reduction potential, no doubt. Here, the representation is little different. Here, this is MnO4 minus / Mn2 plus. Here, this is the oxidation state of just the manganese. Here, this negative sign is not only for the manganese, it is also for oxygen. So from this representation, we have to find the oxidation state of manganese alone. How to find the oxidation state of manganese? The representation is MnO4 minus. So this is the formula, right? And here we have only one manganese and we don't know the oxidation state or the charge of the manganese. So it is considered to be X. And how many oxygen atoms we have? 4 oxygens, right? And what is the valency or the oxidation state of oxygen? You have studied in your 11th standard. What is the oxidation state of oxygen? -2. So here I have only one manganese, oxidation state of manganese to be calculated. So I'm having it as X. Plus I have 4 oxygen and oxidation state of oxygen is -2, which is equal to this -1 is the total charge on the species, which is, so I'm going to write it right in the right side. So what is the value of X, Kanna? Please simplify that and let me know the value of X. Sandhamil Chelvan? Yes, it is +7. Right? It is not +6, it is +7. Rakshan, you're getting the value of X. Bhumika, Sharmila, if you guys want me to calculate, I'll do it.
X is equal to 7.
Yes, that's it. So here the value of X is +7. So here manganese is in +7 oxidation state and that is getting converted into 2+. So how it is possible? By gaining electron. Mn7+ has to gain 5 more electrons to get converted into 2+. Basically it is gain of electron reduction. So the value is reduction potential. Fine. So this is also true. How about this one? Now here the 3+ is the oxidation state of chromium. Here you have to find the oxidation state of chromium again. Please use the same method to find the oxidation state of chromium. Okay, Sendamil Chelvan's answer is +6, right? Rakshan, is it possible for you to calculate, Kanna?
No, ma'am.
Okay, I'll calculate. Sharmila, Bhumika, please listen. Here, the formula Cr2O72 minus, we have to calculate the oxidation state of chromium. Here I have 2 chromium atoms and the oxidation state to be calculated, I'm having it as X. Plus I have 7 oxygen and the oxidation state of oxygen is -2, which is equal to total charge is -2. So 2x plus into minus is minus, 7 into 2 is 14, which is equal to -2. Now simplify and let me know the value of x.
6, ma'am.
That's it. So chromium is in +6 oxidation state and this is getting converted into +3 again by gaining electrons. So this is a reduction. So this is also a reduction potential. Fine. So all the values are reduction potential. So we can use these values. Okay. And what is the shortcut? Electron will be moving from negative terminal to positive terminal. So here this is gaining electron. So this is reduction. And this is losing its electron. This is oxidation. The metal which is getting oxidized is considered to be the reducing agent. It's responsible for reduction. And the metal which is getting reduced is considered to be the oxidizing agent, which is responsible for oxidation. So for the metal to be the oxidizing agent, then that metal should have the positive reduction potential. That was our point, right? The metal, if the metal has to act as an oxidizing agent, then the electrode potential value has to be positive. Okay, here let us compare the values. Here it is -0.74. Here it is plus 1.51. It is plus 1.36 and it is plus 1.33. And here they're asking for the strongest oxidizing agent. For the strongest oxidizing agent, the value has to be more positive, right? Among these 4 values, which is the more positive value? Which is more positive value? Which got more positive?
1.51.
Very good. 1.51. So 1.51 is the more positive value, which means option 1 is ruled out. It is for chlorine. And option 2 is also ruled out. So this 1.51 is for MnO4 minus and Mn2 plus also. So from C and D, we have to identify which is the right answer. According to our inference, if the metal has to be the strongest oxidizing agent, the electrode potential has to be more positive, right? So here we have 2 species here. For a 1.51, here we have 2 species, which is MnO4 minus and another one is Mn2 plus. Here the oxidation state of manganese is 2 plus and here the oxidation state of manganese is 7 plus. Among these two oxidation number, check for the higher positive value. That is what our inference is, right? Value has to be more positive. So among these 2 species, which got more positive value? This one, right? Which is MnO4 minus. So 4th one is the right answer. MnO4 minus is the strongest oxidizing agent. Is that clear? So we have 3 steps here. First, you have to identify whether the potentials are oxidation or reduction potential. If it is an oxidation potential, then you have to convert that into a reduction one. Fine. If that is true, then you have to check for the, first of all, you have to infer the metal. If the metal has to be oxidizing agent, then the value has to be more positive. So among these 4 values, we have to find which got the higher positive value. And in that, we had 2 species. Among that 2 species, we have to find which species got higher positive oxidizing agent, oxidation state. Fine, is that clear? Any doubt? Shall we move on to next question then?
Yes, ma'am.
Okay, actually it is a question from JE main. So now we'll discuss similar type of question. Can you guys solve this problem? It is also a question from JE mains. It is from 2017. Here also we are provided with few values and they're asking us to find the strongest reducing agent. It is just the opposite of previous one. Could you please solve this? I'll give you 4-5 minutes. Please solve it. Please come up with the justification also. I want not only the option, but also the justification. is the first step through. Is it okay to use the values? What kind of potential was that? Is it oxidation or reduction potential? Okay, Sendamil Chelvan, you're half the way you're right, but that is not the right answer, Kana. Okay, now tell me, these values are reduction potential or oxidation potential? Yes, all the values were reduction potential. So we can use these values. And what is our inference? If the electron is moving from negative terminal to positive terminal, this metal will get oxidized. The metal which is getting oxidized is considered to be the reducing agent. So for the metal to be the reducing agent, it has to be negative value or it should have the lower value, right? So here we have four values, right? And among these four values, this got the lowest value, which is minus 0.74, which is for this two species, right? So which means first option and third option were ruled out. And here we got two species, right? One is chromium 3 plus and another one is chromium, which is in zero oxidation state. And what is our inference for the best for the best reducing agent? Value has to be the lesser one, right? Here chromium got 3 plus oxidation state and here chromium got zero oxidation state. So which is the which got lower value, Kana, among chromium 3 plus and chromium? Which got the lower oxidation state?
Chromium.
Yes, so the answer is second option. Is that clear? So it is chromium. Fine. Now we'll move on to next question. Okay. Here, the standard potentials at 25 degrees Celsius for the following half reactions are given against them. See here, they didn't give you the representation, but the reaction itself. Here, Zn2 plus is gaining electron to get converted into zinc, and parallelly, they've provided the electrode potential also. So this is the reduction reaction. So this is the reduction potential. Okay. So the reduction potential is minus 0.762 volt. And here also this is the reduction reaction and the value given here is reduction potential and the value is minus 2.37 volt. Here it is type error. I've given the minus symbol here. Okay. So it is minus 2.37 volt. Fine. Actually the question is if zinc dust is added to a solution of magnesium chloride. See, I have a beaker full of magnesium chloride solution. Okay. Here, if the solution is magnesium chloride, we'll be having a lot of magnesium ions and chloride ions. Okay, fine. Into which you're adding zinc dust. Zinc dust is nothing but zinc powder. Okay, zinc metal we are adding in a powder form. So it is in zero oxidation state. Fine. Now we have to find what kind of reaction or what kind of process is actually happening inside this beaker. Option D is magnesium is precipitated. Option C, zinc dissolves in solution. Option B, zinc chloride is formed. Option A, no reaction will take place. Okay. Before getting to the option, we have two reduction potentials, right? From this, we can infer so many things. Among zinc and magnesium, which is considered to be anode and which is considered to be cathode. If you connect magnesium and zinc, among these values, from these values, you can predict which is anode and which is cathode, or the metal which is getting oxidized and which is getting reduced, right? Could you please tell me which metal can get oxidized and which will get reduced?
Zinc is the anode, ma'am.
Very
Magnesium
good,
is the
Sana.
cathode.
Very good. So here magnesium got the lowest value. So electron will be moving from magnesium to zinc. Okay. So because magnesium got the lowest value, the electron will be moving from lowest value to higher value, right? So here, if you connect magnesium and zinc, then zinc will get reduced. If there is any Zn2 plus ion, then that will get reduced to zinc, and if there is any magnesium atom, then that will get oxidized to magnesium 2 plus. That is what our inference is, right? Electrons will be moving from magnesium to zinc, which means zinc will get reduced. So in a system, if there were any Zn2 plus ion, then that will gain 2 electrons to get converted into zinc. And in a system, if we have magnesium atom, then that will lose its electron to get converted into Mg2 plus. So this should be our inference. Now let us come to this reaction. In the system, we have only magnesium 2 plus ion. And what is our inference? If there is any magnesium atom, it will get oxidized. Here we have no magnesium atom. We have only magnesium 2 plus ions. So here nothing is going to happen. And similarly, the inference is if there is any Zn2 plus ion, it will get reduced to zinc. Here actually we have zinc atom and we have no Zn2 plus ion. So that reaction is also impossible. So if you connect these, or if you dissolve, or if you add zinc powder inside this magnesium chloride solution, nothing will happen. So answer is no reaction will take place. Okay. See, what is the option D? Magnesium will get precipitated. What is precipitation? If magnesium 2 plus ion gains 2 electron, it will get converted into magnesium as solid. This is called precipitation. But the inference is the oxidation and not reduction. So this is impossible, right? And the third option is zinc will get dissolved. How it will get dissolved? If the zinc atom converted into Zn2 plus by losing electron, then this is dissolving. So actually, if the Zn is in atomic level, or if it is in zero oxidation state, it will not get dissolved. If the oxidation state changes from 0 to 2 plus, then only then it will get dissolved. Okay. So for the zinc atom or the zinc to get dissolved, it has to get oxidized. But the inferences, it will get reduced. So option C is also ruled out. Option B is zinc chloride is formed. That is also impossible. How the zinc chloride will form? Actually, zinc has to get converted into Zn2 plus, after which Zn2 plus has to combine with two chloride ion to get converted into zinc chloride. This process itself is not happening. So zinc chloride will also not form. So second option is also ruled out. So answer is first option. No reaction will take place. Is that clear? You're getting my point? Shall we move on to next question?
Yes, ma'am.
Okay. Here we are provided with the reduction potential of 3 species, and they're asking us to arrange these elements in the order of reducing power. Best reducing agent to least reducing agent. Easy. Very simple. Please try, Kana. Let me know the right option. Okay, Sendamil Shelvan's answer is option A.
Ma'am, option 1.
Option 1. Okay. Could you please justify your answer?
Ma'am, the least value is minus 3.03, ma'am. And the highest value is 0.52, ma'am. We are arranging it, ma'am. So we are getting first option, ma'am.
Okay. The metal which got lowest reduction potential will get oxidized, and that will be the best reducing agent, right? So Y2 plus got the lowest value, which is minus 3.03. So it will get oxidized, and that is the best reducing agent. So answer is option A, right? this question. This you can try. Definitely, I know you'll crack this question. Here they're asking for the strongest oxidizing and reducing agents.
Option A.
Yes, it is option A. Shall we move on to next question?
Yes, ma'am.
Okay. Here we are provided with electrode potentials, and from the values of electrode potential, we have to predict which of the following reaction cannot occur. Cannot occur. So check for the values. Is it reduction or oxidation potential? That should be your first step. Okay. After which, please check the options and
Sure.
find which
Ma'am.
reaction cannot occur.
Option A.
Option A. Rakshan's answer is option A. How about Bhumika, Sharmila, Senthamil Chelvan? Senthamil Chelvan, what is your answer, Kanna? Okay, so here the values are reduction potential. So we can use these values. In first reaction, let us observe the reaction. Here, copper sulfate, where copper is in +2 oxidation state, it is reacting with silver, which is in 0 oxidation state. So this copper 2 plus is getting converted into copper, and silver, which is in 0 oxidation state, is converted into +1 oxidation state. So here, copper is gaining electron, so it is reduction, and silver is losing its electron, which is oxidation. That is what the inference, right? And from the value, let's see, what is the value of copper? Reduction potential of copper is 0.34 volt, and the reduction potential of silver is 0.80 volt. So we know the shortcut as electron will be moving from smaller value to bigger value, right? So according to the inference, silver will get reduced and copper will get oxidized, right? But in this reaction, it is just the opposite, which is wrong. So this kind of reaction will not occur. Okay. Shall we proceed? Okay, fine. So these are all the applications, that is physical significance of electrode potential. So we have seen so many applications of electrode potential, right? But all these electrode potentials were standard electrode potential. See, in this problem also they have given the standard electrode potential. What is mean by standard condition? What is standard condition? We have discussed that
1
also.
atmospheric pressure, ma'am.
Very good.
25 degrees Celsius. 1 molarity, ma'am.
Very good. The important part is the concentration. Concentration of the electrolytic solution has to be 1 molarity. So if you dip a metal in its own electrolytic solution, for example, it is a metal M and the solution contains Mn plus ion, and if the concentration is 1 molarity, and if you are connecting this unknown metal with your She, the standard hydrogen electrode, we can find the reduction potential of this metal, right? Here, concentration has to be 1 molarity, temperature has to be 25 degrees Celsius, and pressure has to be 1 atmospheric pressure. So under this condition, the value measured here is your standard electrode potential. Okay. If suppose I have zinc rod, and this is dipped inside a zinc sulfate solution of 1 molar concentration. Okay. And I need to know the reduction potential of zinc. We know we have that tabular column, right? So from the tabular column, we can find the electrode potential of zinc. So actually, the data is electrode potential, that is reduction potential of zinc is minus 0.76 volt. So this is the standard value, Kana. We need not memorize this. From the tabular column, we know if you dip the zinc metal in zinc sulfate solution of 1 molarity, then the value will be minus 0.76. But if you dip zinc rod in zinc sulfate solution of any other concentration, not 1 molarity, of any other concentration, for example, of 0.1 molarity, then value will not be minus 0.76. And we doesn't have the standard values of electrode potential of all the concentrations, but we can calculate the potential of non-standard condition. See, we don't have ready-made data for non-standard condition, but definitely we can calculate. Okay, so to calculate the electrode potential of non-standard condition, we have a special equation called Nernst equation. Nernst equation. Okay, so we can write the equation. See, you have to be careful with the representation. Kana, what is capital E naught? What is capital E naught? Capital E is the potential, and in the subscript, I didn't write anything, which means that
Electrode
is the
potential.
very good, Kana. It is the electrodes potential, and I've written the naught. So it is the standard electrode potential, right? And just now we have discussed this Nernst equation is to calculate the electrode potential of non-standard condition. So left side I'm going to have just capital E. So it is the electrode potential at non-standard condition, which is equal to E naught, which is the electrode potential at standard condition minus R into T divided by N F ln. See, all the potentials we are talking about is reduction potential. For example, I have N plus, and this ion has to gain N electrons to get converted into metal M. So this is the reduction reaction, right? And in this reaction, this is the product. So here it is the concentration of the product divided by concentration of the reactant. That's it. This is the Nernst equation. So let us find what is R, T, F and all that. Okay. We know what is capital E and what is capital E naught. E is the reduction potential of any metal at non-standard condition, and E naught is the electrode potential of any metal at standard condition minus R is the universal gas constant. Could you please tell me the value of R? We have so many values of R, but I want the value in terms of joules, which is very famous one. You don't remember? 8.314 joule per mole per Kelvin. Okay, and T is the temperature, and it is 25 degrees Celsius. Can you please convert that into Kelvin? We shouldn't use the value in degrees Celsius. Please convert 25 degrees Celsius into Kelvin. Have to convert to Kelvin. You have to add 273 to 25 degrees Celsius.
298.
That's it, 298 Kelvin. Kana, what is F? Just now we have seen. What is F? It is Faraday. And what is the value of 1 farad? 96,500 unit is coulomb per mole. And N is number of electrons involved. See, that is very easy. For example, in the case of zinc has to get converted into Zn2 plus by losing electron, or Zn2 plus has to gain 2 electrons to get converted into zinc. So the number of electrons involved is 2. In the case of silver, I have silver rod or something. I'm going to dip the silver metal in a solution which contains Ag plus ions. Okay. So here, what is the number of electrons involved? So Ag plus ion has to gain electron to get converted into Ag, which is silver in elemental form. How many electrons has to be gained by Ag plus? Only 1 electron, right? So in this case, the number of electrons involved is 1. So number of electrons involved will be varying from metal to metal. So we cannot generalize that, but N is the number of electrons involved. Okay. And is it possible for us to convert ln into log? What is ln? Which is equal to 2.303 log, right? Now we're going to substitute the values of R, T and F. So which is E is equal to E naught minus 8.314 joule per mole per Kelvin. And what is the temperature, Kana? 298 Kelvin divided by N into, what is the value of F? 96,500 coulomb per mole. And I'm going to convert this ln into log, which is 2.303 log. Here, what is the product? This metal is the product, right? So concentration of metal divided by concentration of metal ion. What is the physical state of metal? What is the physical state of metal? Is it solid, liquid or gas?
Solid.
Solid. For any solid, the concentration is unity. Okay. So for solids, for pure solid and for pure liquid, concentration is unity, which means here this term will be 1, right? And also we can simplify these numbers and we can cancel this per mole and per mole, Kelvin per Kelvin and all that. So here the unit will be joule by coulomb. Actually, joule by coulomb is nothing but volt. Okay, so this complete term will be in the volt unit. Okay, so I'm going to simplify all those numbers, Kana. Capital E is equal to E naught minus, if you simplify all these values, you'll end up with the value 0.0591 divided by N log. In numerator, since the metal is in solid state, the concentration is 1 divided by concentration of metal ion. That's it. So this is the final Nernst equation. This equation can be used to calculate the electrode potential, which is in non-standard condition. Okay, fine. So initially I've told no, if the zinc is in Zn2 plus solution and the concentration is 0.1, then the value will not be minus 0.76, right? But we can calculate for this. So shall we so now we'll calculate the value of this system by using the Nernst equation. Shall we? Shall we calculate the electrode potential of this unknown, for this zinc system at non-standard condition?
Yes, ma'am.
Okay. So what is the formula? E, which is equal to E naught. Here we are talking about zinc, right? So I'm going to represent it like this. Minus 0.0591 divided by N log concentration of metal, which is 1, divided by concentration of metal ion. Here the metal ion is Zn2 plus. That's it. What is the value of E naught? Standard reduction potential of zinc is? Standard reduction potential of zinc is? It is in the board. So what is the standard reduction potential of zinc? It is minus 0.76, right? Minus 0.76 minus 0.0591 divided by number of electrons involved in this cases. So here we have two species. One is Zn2 plus and Zn. So how many electron has to be gained by Zn2 plus to get converted into zinc? What is the number of electrons involved here? 2. Log 1 by, what was the concentration of the solution? What was the concentration of the solution? It is 0.1, right? It is 10 power minus 1. That's it. So if you simplify these values, you'll end up with the reduction potential of zinc under non-standard condition. So if you want to simplify, you can round this value to 0.06 divided by 2 log. If you take this 10 power minus 1 to the numerator, it is 10 power plus 1. And what is the value of log 10? The value of log 10 is? Value of log 10 is? You have to know the log values for at least a few numbers, Kanna. See, as far as log is concerned, we have to know a couple of formulas and values. See, what is log A into B? It is log A plus log B, right? If it is log A by B, then it is log A minus log B. It is log, if the value is log A power B, then it is, you have to bring the power in the front. So it is B log A. Okay. And similarly, value of log 10 is 1. Value of log 100 is? Value of log 100. Easy. How this 100 can be written as 10 power 2, right? So it is log A power B. So I'm going to write it as B log A, 2 log 10. So here 2 log 10 is 1, so it is 2. So log 10 is 1, log 100 is 2. So what will be the value of log 1000? Log 1000.
3 log 10.
A 10 power 3, which is 3, right? See, these are all the things you don't want to memorize. If you know if the value of log 10 is 1, then automatically we can calculate this. And how about log 10 power minus 1 or log 1 by 10? Or value of 0.1? 0.1 can be written as log 1 by 10. Or this can be written as 10 power minus 1. Or this can be written as minus 1 log 10. So what is the value? It is just minus 1, right? Similarly, 0.01. What is the value of 0.01? 1 by 100, or log 10 power minus 2. So it is minus 2 log 10, which is minus 2. That's it. Fine. So these are all the values you don't want to memorize. Just from the logic we can find. But we have to memorize these values. Log 2. Do you know the value of log 2? Very easy. Log 2. 0.3010. Log 3. Log 3. 0.4771. Similarly, log 5 is 0.6989 and log 7 is 0.8450. We just need to memorize only these four values. That's it. If we know these four values, you can calculate or you can simplify any log value. Okay, you can find log, you can find anti-log. If the value is so complicated, also we can solve it just by memorizing these four values and these formula. Okay, right. And in future, I'll teach you how to do that also. And let's come to this problem. Here we have log 10 and we know the value of log 10 is 1. So this is 1. And if you cancel this, it is 0.03. If you simplify these two stuff, we'll be getting a value in negative. So what is the value, Kana? It is minus 0.7. 0. 0.79 unit is volt. That's it. Any doubt? Fine. So what is the purpose of this Nernst equation? What is the purpose of this Nernst equation? It is to find the electrode potential under non-standard condition. If your solution is not, if the concentration of the solution is not 1 molarity, then definitely you can use this Nernst equation to find the electrode potential. Okay, fine. This is not only for the electrodes, these Nernst equations can also be applied to cells also. What is cell? Definitely we'll be having two electrodes. If any of the electrodes is under non-standard condition, or if both the electrodes were in non-standard condition, then you can use Nernst equation. And I'll give you the formula or Nernst equation for cell also. It is very similar to your Nernst equation for electrode. E is equal to E naught cell minus 0.0591 divided by N log. Here initially we had concentration of the product. Here the product was metal whose physical state is solid. So I am having it as 1 divided by concentration of metal ion, which is the concentration of the reactant. Similarly, we can have it for cell also. E cell. E cell is nothing but the cell potential under non-standard condition, which is equal to E naught cell minus 0.0591 divided by N log concentration of product divided by reactant. So this is the Nernst equation for electrode and this is Nernst equation for cell. Very simple. Okay. So shall we do one problem in Nernst equation for cell so that it will be very comfortable for you? Shall we? Why, Kana? What happened? Why you guys are very quiet? What's happening?
Yes, ma'am.
Okay. So I'm going to give you a problem. Can anyone read this question? the question, Kanna. You just read the question. We'll solve it together.
Okay, ma'am.
Hmm. So the question is, they're asking us to write the Nernst equation and they're asking us to find the EMF of the cell. EMF is nothing but it is the potential, and they're asking about the potential for cell. And is the cell is in standard condition or not? See, this is the cell representation, and we know
No, ma'am.
yes, it is not in standard condition. Here, the concentration is not 1 molarity. So they're asking us to find the cell potential at non-standard condition. And of course, we have to use Nernst equation. And formula of Nernst equation is E cell, which is equal to E naught cell minus 0.0591 divided by N log concentration of product divided by reactant. See, this is just the cell representation. Here we don't know the concentration of product, or which is the product and which is the reactant. So to find all those products concentration, reactants concentration, number of electrons and all that, first we have to write the anode reaction separately, cathode reaction separately, and you have to add both the reactions to find the redox reaction. And from that redox reaction, we'll be finding the concentration of product and the reactant. Okay, so the first step is anode reaction. Among magnesium and copper, which is anode, Kana? Among magnesium and copper, which is anode? See, from cell representation, the double vertical line is considered to be your salt bridge, and left side will be having anode and right side will be having cathode, right? So among zinc and copper, which is anode? Which is anode?
Magnesium.
Very good. Magnesium is anode. So anode reaction is just the oxidation reaction. So magnesium will get oxidized to Mg2 plus. So magnesium is in solid state. It loses 2 electrons to get converted into Mg2 plus, which is an aqueous medium. And the cathode is copper, where reduction occurs. Their copper 2 plus is getting converted into copper. So copper 2 plus has to gain 2 electrons to get converted into copper. So this is the anode reaction and this is the cathode reaction, and we have to add both the reactions. So to add those reactions, we have to cancel the common terms. Here only the number of electrons are common. If the electrons are not common, then you have to make it common. How to do that? By just cross multiplying. So you have to multiply the first equation with the number of electrons of second equation, and you have to multiply the second equation with number of electrons of first equation. Here that is not necessary because already it is common. We can cancel those electrons. Now we have to write the remaining parameters. So left side, in first reaction I have magnesium, which is in solid state, and in second reaction I have copper 2 plus ion, which is in aqueous medium, which gives magnesium 2 plus, which is in aqueous medium, gives copper, which is in solid state. That's it. So this is the redox reaction. So here, how many electrons were involved in this total process? See here, magnesium lost its 2 electron, and those 2 electrons were gained by copper. So you should not calculate it as 4 electrons. It is just the 2 electron. So the 2 electrons were lost by magnesium, was gained by copper. Okay. So here number of electrons involved is 2. Fine. And here product is magnesium 2 plus ion and copper. And the reactant is magnesium and copper 2 plus, right? So E cell, which is equal to E naught cell minus 0.0591 divided by 2, which is number of electrons involved, into log. Here the products are concentration of magnesium 2 plus and the copper divided by concentration of magnesium and concentration of copper 2 plus. Okay, so here we have to know the value of E naught cell. Could you please tell me the formula of E naught cell? Formula of E naught cell? Formula of E
E
naught
naught
cell?
equal to E naught cathode minus E naught Anode, ma'am.
That's it. E naught cathode minus E naught anode. I'll tell you the values of magnesium and copper. This will be provided in your problem itself, so you need not memorize these stuffs. So the electrode potential, specifically the reduction potential of magnesium is minus 2.37 volt, and the reduction potential of copper is 0.34 volt. And from this representation, we found anode was magnesium and cathode was copper. So you have values. Please simplify and tell me the value of E naught cell. What is the value of E naught cell? Cathode values 0.34 minus 2.
2.7.
Yes, 2.71. So it is 2.71 minus 0.0591 divided by 2. You can round it off to 0.06 also. It is fine. Anyways, it is easy to cancel, so no issues. And what is the concentration of magnesium 2 plus? It is given in your problem. What is the concentration of magnesium 2 plus? Concentration of magnesium 2 plus is
10 power minus 3 molar.
Very good. It is 10 power minus 3 molarity. And concentration of copper. See, here copper is in solid state. So if the system is in solid or liquid, then the concentration is unity. So you need not include this. And similarly, here the concentration of magnesium is also 1 because magnesium is in solid state. And in denominator, we have one more parameter, which is the concentration of copper, which is given as 0.0001, which is 10 power minus 4. That's it. If you simplify these values, you'll end up with the value of E cell, which is the EMF of the given cell. Okay, is that clear? Is that clear, Kana?
Yes, ma'am.
That's
Yes,
it.
ma'am.
So today we have discussed the physical significance of electrode potential, from which definitely you can expect a problem, and also Nernst equation, equally important. So you can expect problem from Nernst equation also. They may ask you to find the electrode potential of electrode or cell. Anything is possible. So anything can be expected. So please solve and practice this kind of problems, Kana. You may expect questions from electrode potential also, and from your Nernst equation also. Okay, and in next class we'll be discussing a few topics like molar conductivity, equivalent conductivity, conductance, conductivity, cell constant, and all that. Okay. Anyways, we have done with 50-60% of the chapter, and we'll discuss the next half of the chapter in our next class. Okay. Do you have any doubt till now? Any doubt, Kana? Fine. Okay, if you have no doubt, then Sendamil Chelvan came up with the value, which is 2.68 volt. Brilliant. Yes, that is the right answer.